Welcome to our exploration of 5G technology, the next wireless revolution reshaping how devices connect and communicate. In this introduction, I'll briefly set the stage for what 5G is, why it matters, and how it enables new applications from smart cities to industrial automation, giving you a high-level sense of the opportunities we'll examine in the slides ahead. This slide asks a simple question. What is 5G? Put plainly, it's the fifth generation of mobile networks, a global standard that goes beyond faster phones to enable massive device connectivity and new services. Think of it as a unified platform designed to support everything from low-latency robotics to dense IoT deployments across the world. Here we trace mobile networks from 1G to 5G, showing how voice-only analog systems evolved into today's ultra-fast, massively connected networks. The timeline highlights how each generation added capabilities, text and digital voice, mobile internet and apps, high-speed streaming, and now 5G brings ultra-low latency and huge device density, unlocking entirely new use cases and industries. This slide outlines the core features that define 5G, starting with ultra-fast speeds and moving to near real-time responsiveness with sub-millisecond latency. It also emphasizes massive device connectivity, support for mission-critical reliability, and overall network robustness, so you can see why these technical improvements matter for practical services like autonomous vehicles and industrial control. Why does 5G matter? Because data volumes are exploding, and new applications need both bandwidth and low latency. This slide connects the dots between exponential data growth, enabling technologies like AR and autonomous systems, and the smart infrastructure that 5G makes possible, while pointing out the large economic upside from new services and efficiencies. This comparison shows how 5G stacks up against 4G and earlier generations in speed, latency, frequency range, and device density. The key takeaway is that 5G delivers orders of magnitude improvements, much higher peak speeds, dramatically lower latency, and the capacity to support far more devices per square kilometer, which together enable use cases that weren't feasible before.
Now, let's look at how 5G actually works at a technical level. It uses higher frequency radio waves, including millimeter bands, dense small cell deployments to overcome range limits, OFDM modulation to maximize efficiency, and beamforming to focus signals toward devices. Together, these advances raise throughput, reduce interference, and improve reliability compared with prior systems. This slide highlights three standout 5G technologies: OFDM, which splits data across carriers for efficient transmission; massive MIMO, which multiplies capacity using many antennas; and network slicing, which creates customized virtual networks for different needs. Each technology solves specific challenges: efficiency, scale, and flexibility, so operators can tailor performance for diverse applications.
5G spectrum spans low, mid, and high bands, each with trade-offs. Low band below 1 GHz offers wide coverage and building penetration. Mid-band balances speed and range for urban and suburban areas. And high-band millimeter waves deliver ultra-fast throughput, but over shorter distances. Understanding this spectrum pyramid explains deployment choices and performance expectations. This overview of 5G network architecture breaks the system into 4 layers: user equipment like phones and IoT devices, the radio access network of base stations, the 5G core with cloud-native functions, and edge computing nodes that bring processing closer to users. Together, these elements reduce latency and enable scalable, service-based network operations. Here we compare two deployment approaches: non-standalone, which uses 5G radio with an existing 4G core for faster rollouts but limited capabilities, and standalone, which implements a full 5G core for maximum performance, slicing, and low-latency features. The slide shows how operators transition from quick initial deployments to fully capable 5G networks. This slide lists the core components of the 5G system: user equipment that connects to the network, NG-RAN base stations that provide radio access, core network functions like UPF and AMF that manage sessions, and support functions for data management, policy, and security. Together, these components enable flexible, service-oriented connectivity across many device types. Small cells and densification are central to 5G coverage strategies. Instead of relying on a few large towers, networks deploy many low-power transmitters across urban blocks to boost capacity and speed. The images illustrate how a dense fabric of small cells can dramatically improve performance in high-traffic areas by bringing signals closer to users and devices. Network slicing creates multiple virtual networks on shared physical infrastructure, giving each slice tailored latency, bandwidth, security, and reliability. This slide explains how slicing partitions resources, so mission-critical services, consumer broadband, and IoT applications, can run independently yet simultaneously on the same network, simplifying management and improving efficiency. Edge computing in 5G places compute resources near users to minimize travel distance for data, cutting latency, and enabling real-time applications. By processing data locally, networks reduce bandwidth usage and support use cases like autonomous vehicles, AR, VR, and industrial automation, where milliseconds matter and only relevant information needs to be forwarded to the cloud. This slide connects 5G to the Internet of Things, showing metrics like millions of devices per square kilometer, multi-year battery life for low-power sensors, high reliability for critical IoT, and massive device counts expected globally. The message is that 5G provides the density, longevity, and dependability required to scale ubiquitous IoT across smart cities and industries. Benefits to businesses are broad. 5G enables new business models and revenue streams, supports scalable networks that adapt capacity dynamically, improves operational efficiency via cloud-native architectures, and enhances performance with faster response times and higher reliability, all of which help organizations innovate and reduce costs simultaneously. 5G is transforming industries across the board. In automotive, it enables connected vehicles and real-time navigation. In healthcare, it supports remote surgeries and monitoring. Entertainment benefits from cloud gaming and immersive AR/VR. And manufacturing gains smart factories and predictive maintenance. Each sector uses 5G's, low latency, and connectivity in distinct, impactful ways. On the consumer side, 5G unlocks cloud gaming with console-quality experiences, seamless augmented reality interactions integrated into daily life, and near-instant downloads for large media files. These everyday applications highlight how lower latency and higher throughput translate into noticeable improvements in entertainment, shopping, and general device responsiveness. The global rollout of 5G is uneven, and this bar chart illustrates regional differences in deployment scale. Some regions have advanced coverage and dense networks, while others are still ramping up. The visual helps explain why user experience and available services can vary substantially depending on local infrastructure and rollout priorities. This Smart Cities case study shows real-world 5G uses like intelligent transportation where traffic signals adjust in real time, sensors that monitor infrastructure, HD surveillance for public safety, and environmental monitoring for air quality and noise. Together, these applications demonstrate how connected systems improve urban efficiency, resilience, and citizen services. In healthcare, 5G enables remote diagnostics with high-definition video, connected ambulances that stream patient data en route to hospitals, surgeons performing remote procedures with haptic feedback, and continuous wearable monitoring analyzed by AI. The slide highlights how reduced latency and reliable connectivity expand access to specialized care and improve emergency response. Industrial automation benefits from 5G through real-time robotics control with sub-millisecond responsiveness, predictive maintenance across thousands of sensors to reduce downtime, and augmented workforce tools like AR glasses and digital twins that boost productivity. These examples show how connectivity transforms manufacturing from static operations to flexible, data-driven production.
Security in 5G networks include stronger authentication, improved encryption, and isolation through network slicing. but the technology also introduces challenges like a larger attack surface, software vulnerabilities, supply chain risks, and IoT device security. The slide emphasizes that security must be integrated across architecture, devices, and operational processes to protect these distributed systems.
Deployment challenges remain significant. Infrastructure costs and densification investment are high. Spectrum availability is limited and requires regulatory coordination. Technical issues like wave propagation and building penetration persist, and device compatibility during the transition creates mixed capability networks that operators must manage carefully. Addressing rural and urban gaps requires tailored approaches. Urban solutions rely on dense small cell deployments, building-mounted equipment, and integrated street furniture to meet capacity demand, while rural strategies use low-band spectrum, dynamic sharing, fixed wireless access, and satellite integration to extend coverage to underserved communities and reduce the urban-rural digital divide. 5G also has environmental and societal implications. It can be far more energy efficient per unit of data than previous generations, support smarter sustainability through connected sensors and grids, improve emergency response capabilities, and expand accessibility to remote education and healthcare, helping reduce barriers to essential services in underserved areas. Looking ahead, the roadmap moves from 5G advanced in the near term to satellite integration and pre-6G research, and eventually towards a 6G era, with even lower latency and new capabilities. This slide frames the evolution as a continuous progression of higher efficiency, broader coverage options, and foundational research that will enable the next leap in connectivity. The 5G ecosystem depends on many key players, from network equipment vendors and chipset makers to operators and standards bodies. This slide shows logos as examples and explains that collaboration among these organizations drives interoperability, innovation, and the widespread deployment needed to realize 5G's full potential across markets.
In conclusion, 5G represents a foundation for innovation, offering ubiquitous connectivity and acting as an economic catalyst that enables new industries and business models. The closing message ties together how the technology unlocks possibilities that weren't previously feasible and invites the audience to think about practical next steps for adopting and leveraging 5G capabilities.